Hello, we are Team 20, and our project was testing anisotropic materials in the elastic region. Our group members are Alexa Corsi, Isan El Nunu, Jonathan Groes, Ronaldo Herrera, Anthony Nigrin, and Christopher West, with advisors Dr. Wang, Dr. Tong, and Dr. Zhang. As an introduction to our project, as anisotropic materials become more prominent in today's material billet, there is an ever-growing need to understand how these materials behave, particularly in the elastic region of the stress strain curve. Our team worked to develop and standardize the testing procedures needed to fully characterize all the elastic constants of general anisotropic materials. This required this required designing mechanical clamps to work with an instrument testing machine to apply shear and tensile forces in a single plane. Once a force was applied and isolated to a single plane, strain measurements were taken based on the relationships in the general compliance matrix, which allowed us to solve for all necessary constants.
Orientation and isolated plane relationships. Because anisotropic materials typically do not have trivial directionality, it is important to define the orientation of each material for continuity. The stiffest orientation-based standardized compliance matrix, which is abbreviated as STFOS, give us a standardized way to orient the materials so long as these conditions are met. The first condition is the x1 axis makes S11 reach the global minimum. For example, the stiffest direction in the whole orientation. Second condition is the x2 axis makes S22 global minimum within the plane perpendicular to x1 axis. The third condition is the x3 axis complies with the right-hand coordinate system rule. The fourth condition is S14 and S25 reach their minimum values under above conditions. In addition, the STFOS compliance matrix reduces the 21 general compliance matrix constants to only 18 constants, which can be seen in those two matrices right here. We can see that the S15 and S16, along with the S24 constants, go to 0. In order for us to transition from here to this matrix, there's only one condition. That condition is it will only hold for a single loading plane. And we can afterwards get those relationships between strains and stresses. As for our objectives, we develop a testing procedure to find all 18 elastic anisotropy constants in the STFOS matrix. Design and manufacture instrument clamps to apply shear and tensile forces in a single loading plane and create a uniform stress state, which can be seen in this displacement plot right here. We know that we start here and increase along the y direction to this blue area. This makes sense in a tensile test because we stretch, and along the stretching, along the y direction, we know the blue is higher than the red, which creates a uniform state stress. The last objective is prove the clamps can isolate a single plane of stress and find results that are within 5% standard error.
We had to design two clamps for getting all the constants in the general compliance matrix. We needed tensile clamps and we needed shear clamps. On the bottom left-hand side, you'll see an FEA analysis of the tensile clamp, and on the bottom right-hand side, you'll see an FEA analysis of the shear clamp. And these are analysis of displacement. So we 3D printed these clamps, and on the left-hand side, the balsa wood sample shear test, that is an example of our shear test. And we were testing balsa wood in that case. So how we got these clamps to be, or how we confirmed that their standardized error is under 5%, and we confirmed that they only apply force to a single loading plane, is we tested the balsa wood, for example, and then we got shear modulus, and then we compared the published results of shear modulus to balsa wood, and we found that our error was under 5%. So that's how we confirmed their clamps were good. So those are our clamps. And then now we're going to look at testing procedures. So on the left-hand side, the user test procedures, that is a complete user manual for anybody wanting to test all, we'll have all the tests to find all 18 constants in the general compliance matrix. So that assumes that you can measure a single strain per test. If you can measure multiple strains, you can cut down all the tests you need, but assuming that you can only measure one, you have to do all those tests to find every single constant. And that only holds if you can isolate a single plane, a single loading plane, and that also is in the STFOS compliance matrix as well.
Yeah, and the method that we use to measure displacement and strain of our samples was through the use of digital image correlation, also known as DIC. This is a full field non-contact optical technique, non-invasive, so we aren't touching or obstructing the sample or testing equipment as we're measuring the strains. The way that DIC works is you paint a speckle pattern on our sample, and we track those speckles as the material is deforming through images at specific increments of time. Later on, I'll show you the video of our setup, but the software we used to do DIC were Vic2D and Ncore, along with a combination of MATLAB and ImageJ to help with the image processing. DIC was very important in helping us isolate the strains in multiple directions. Here in the two images, you can see two different directions, X direction and the Y direction, and you can really isolate any direction. So Isan will now be pulling up a video of our DIC setup with our DSLR camera. We have a light source mounted on top with a remote shutter so that we are not obstructing the camera. We focus the camera perpendicular to the sample and make sure we get the lighting properly focused. And we also use an instron to measure the forces that we're applying and get the subsequent strains. So that's DIC.
And in conclusion to our project, our idea to find elastic constants of anisotropic materials by defining the stress and strain relationships of each constant under a single loading plane and creating the subsequent testing procedures will hopefully further advance the area of anisotropic material testing. This procedure is repeatable and can be applied across all fields of anisotropic material testing. Although our clamps performed adequately for our testing purposes, future work may focus on redesigning our clamps to accommodate stronger and thicker materials.